Hi everybody, this is Mrs. Ellsworth. Just a reminder that our main goal of this unit and some of the other units too is that we want to create a videotape with a news commentator speaking over an event, a sports event, where we are talking about the physics. And you can't have a whole lot of sports without friction. Because again, friction is things like traction, and friction is things that slow you down, speed up, and that's all about life's forces and motions. Okay, so in class we'll watch the video, the Mu You Do, and I've also got that posted on Google Classroom. But so we're going to, so specifically talking about frictional forces, I've got two goals in mind. One is to of course learn about the mu of your shoe lab, and then also to do some calculations about mu, which is the coefficient of friction. So let's get started. Let's talk about this. Okay, so you can see this person's happy face. They're pulling a shoe across the ice and it's easy speasy, and now they're doing it across some gritty sand, and it looks like it's a little bit of anguish there, so it's taking more effort for them to do that. So that's kind of the whole idea about it, about what is a shoe sliding against, okay, because those two surfaces matter on what mu is. Mu, the coefficient of friction. And so why do some sports require special shoes? Notice that the wrestling shoes are so much different than like some of the track shoes that we run on, that the ones, also football cleats, court shoes, volleyball shoes. They have all got different types of features with them. And so why is that? Why do different features on shoes be useful in different sports? So those are some of the ideas that we're going to be looking at in this unit. Okay, so I'm going to draw some forces on this shoe. What is the total force on this shoe? And so let's look at that for a moment here. Let me get some lines going on here. Okay, so from the center of it, I've got a force that's being pulled to the right. Okay, I've also got a frictional force. Okay, and that frictional force depends on a couple of different things. I've also got the force of gravity, and then also equally, since it's not levitating or going through the ground, let's estimate that those are the same size, and that those would be, let me get this here, this would be the force of gravity, this would be our normal force, okay, and this is our force that we're applying to it, that's an A, and here this would be our frictional force. So we can calculate what the net force is. If it's going to accelerate this way, then this force will be larger. Okay. Now, if this force actually wasn't larger, okay, if we got it to be the same size as that one, I'm just estimating that they're the same size, okay, then we'd be at a state where it's not accelerating. So that would be what we're actually trying to achieve when we're doing this lab, because then this is going to be just, you're pulling it just enough to get it moving and to stay moving, and then this force here should stay constant on your force meter or on your spring scale. Okay, so that's what our goal is. We're going to figure out what the force, what the mu of the shoe and the surface of the classroom is, and so we're going to measure that. So we got to look at some ideas. Net force, remember, that is total force, and so look at some ideas of what's going on in this. We want our net force really to be 0 because we don't want it to accelerate when we're trying to take some measurements. So let's look at this another way here. Okay, so the force of friction. Okay, we need to measure that, and we weren't doing it by sliding friction, and then also the normal force. Well, you know, how are you going to measure this normal force? Well, if it's equal to the weight of this thing, okay, if it's equal to the weight of it, then we can figure out the normal force by getting the weight. Right? Just holding it with a force meter up in the air, be hanging up there, you're just measuring how many newtons that it is. Okay, how do you figure out the frictional force? Well, we can't really measure that one very easily either, but we can measure this one, and if we get it to just to barely go, keep going where it's not accelerating, then these two forces will be equal. So this one is the normal force, and we'll find it by using the weight. And remember that the weight is measured in newtons. Okay, the frictional force, that'll be the force that we're pulling with, so that's kind of our applied force or else our pulling force. Okay, and that's measured in newtons. Okay, so that's the two measurements that we'll take when we're sliding it across the floor. Okay, so I haven't talked about any independent variables and dependent variables that we're going to use to calculate the mu of our shoes, but anyway, so let's go ahead and look at this. So why doesn't it have any units? Well, the force over force is newtons. They're going to cancel out, so there's going to be no unit. Okay, it's a true ratio. Okay, mu is usually expressed in a decimal form. We'll talk about that. I got a whole table of them to look at. Okay, mu is only valid for the pair of surfaces that's in contact. So if you talk about like a steel ice skate blade across ice, and then take that same pair of skates and try and skate across the carpeted floor, it's different. You can't glide on the carpet. So it changes, once the surface changes, it changes that mu value. Okay, the normal force changes if the surface is tilted, and of course that adds some angled forces, so that would change it too. So if it's tilted, then that changes everything. But for this lab, we will not tilt the floor. Okay, so there are two types of friction. Okay, one is static friction, and static comes from stat, so is stationary, the root word. Okay, so when something is sitting still, okay, it's hanging on there by static friction. And then once it gets moving, then it's called kinetic friction, because kinetic means motion. Okay, so I always tell students in the classroom, take your table that you're on right now and push it with just a couple fingers, push it. Does it take more force to get it started or to keep it going? And they find out every time that it takes more force to get it moving than it does to keep it moving. And that's the difference between these. So static friction is always greater than kinetic friction, even with the same exact surfaces touching. Okay, so for our lab, okay, you're going to find the weight of the shoe. You're going to hang the shoe right there, right? You've got your beautiful looking shoe right here. You'll hang it and you measure it in newtons, right? Either with our spring scales or else with our force meters. Okay, so you'll find the weight, and that's going to be your F sub n for the normal force because they equal each other. Okay, then define the force to barely keep the shoe going at a constant velocity, and that's going to be a sliding friction or else a kinetic friction that's going on right there. And so I should actually put that this is a frictional force, kinetic, okay? Okay, and so we're going to use two different tests with this, and you're going to use the same shoe in this year because we want it to move along right now. And so you're going to do one shoe, okay? And then the one test that you do, this is test one. Okay, you're going to measure it with different weights in it. Measure it at twice the weight, quadruple the weight, and so we want to see how that will affect mu going across the classroom floor. This shoe with no added weight to it will be your control shoe that you're going to make all the comparisons to. Okay, then we'll do a test 2, okay, where you're going to use that same control shoe going across the classroom floor. Okay, but now we're going to put on different surfaces. So what surfaces can you find in our school? And so you're going to have to take some data over that. Okay, so here's our independent variables. Okay, our independent variable for our first test is to change the weight of a shoe. Same shoe, how does that affect the mu? Okay, our independent variable in the second test. Now we're going to take that shoe and we're going to pull it over different surfaces with no added weight to it, and so that we can compare it and see how does this surfaces affect mu. Okay, so analyzing the forces acting on the shoe. You pulled the shoe at a constant velocity. Why? Because you wanted that applied force to be equal to your frictional force. You just wanted to overcome it just barely so it'd be as close as possible to what this frictional force was that you were measuring. Okay, so we want that applied force, that one that you're pulling with, we want that to be as close as possible here, or else it would not be accurate. Okay, this force was about measuring the force of barely overcome friction, and otherwise it won't be accurate. It'll be wrong. So we don't want to accelerate. Okay, static friction can have a few values, okay? You can tug on an object like a shoe and it may not move, okay, because that static friction is holding it there. Sometimes I think about how we get products to stay up, like stay in a certain situation is because we're using static friction to hold it there, okay? You may tug a little bit harder and it may not move, okay, because you haven't overcome it yet. Okay, both forces are not equal, but each force will be equal to static friction. So we can assume that the maximum force on this is the static friction. Okay, it's always greater than the kinetic. Okay, and I just wanted to show you quickly just a table. It's cool. When you look at all these different kinds of systems here that's going on, Teflon against steel, okay, oh, they're even talking about bodies there, but shoes on ice, how that it doesn't have a whole lot of friction here, and especially compared to shoes on wood floor, okay, and then you go and you get it moving, and then once it gets moving, there's a whole lot less friction. Once you get it moving, it's a whole lot less friction. So it just, you know, it's quite interesting when you think about this. So like steel on steel, that could be some moving auto parts. If you don't have it oiled, then it's got a lot more friction than if you do have it oiled. So of course that friction could create problems with you know, like a motor seizing or anything like that. Okay, so we're going to talk next time about what if it's at an angle. How does that change the frictional forces, and how does that change mu? Does it change mu? We'll have to talk about that.